All right, welcome back, everybody. We're gonna pick up where we left off, but just beforehand. So, just as a reminder, so our first homework assignment is due this Sunday. It's several sections, so hopefully you've got started already. But if not, no worries. But ideally, try and get that stuff taken care of sooner rather than later, just so that you don't have to worry about what's. I was just getting confused when I saw the notes. It's like, why did I write this as -5 over 624? And that's not a 624, that's just the page number. Um, and then one other reminder is that we have our syllabus quiz. If you haven't done it yet, the syllabus quiz is due today at 2 p.m. That way I can record all the data for CSN. And please remember, if you don't get 100%, if you don't do it by 2 p.m., then I have to mark you as not participating, which means that you get dropped from the course, which I don't want to do. I don't want to have to do that to anybody. But either way, so last time we talked about, and hopefully everyone got my email and was able to print them off. I'm sorry, it was a little short notice, trying to get them all finished sooner than later. We don't need to worry about 0.7 for a while, so that one's not going to be there. But 0.5 and 0.6 should be hopefully available by this weekend, so you can print it off ready to go on Monday or download it, whatever works. So we talked about how to do all the different types of fraction stuff, how to add, subtract, multiply, and divide. And then we talked very end about the fact that now that we've gone through all the nitty-gritty work, we've gone through the hazing process. Now feel free to use your calculator to simplify fractions for you. But please remember this process and how it works, because this is going to become relevant again once we get to rational expressions with variables inside them. So now with that in mind, we can now talk about linear equations with adding on a little extra paprika or a little cayenne pepper. Maybe this is just some chili powder. Like, which one's spicier, do you think? Cayenne pepper or chili powder? Chili powder? Okay. Maybe I'll make like then cayenne pepper. We don't want it to be too spicy. So some useful facts to know about fractions that we haven't talked about yet is that negative signs can travel within fractions. So that is to say, if you have -1/3, that's the same as -1/3, which is the same thing as 1/-3. All three of those things mean the exact same thing. And so depending on where you need the negative sign, it might be useful to visualize it in the numerator, the denominator, or completely outside the fraction as just a negative sign in front. It all depends. And there's a reason why that works. And if you'd like to see the reason, realize that -1/3 is the same thing as -1 times 1/3. But -1 is the same thing as we learned before. You can write that as a fraction as -1/1. Or you could write it as negative, or you could write it as 1/-1 times 1/3. And so if you do the top one with red, then it becomes 1/-1/3 when you multiply the fractions across. And if you multiply it across in the bottom one with the blue, then you get -1/3, a -1/3, excuse me. So all of these things mean the exact same thing. I just want to make sure that's clear, because that's a very, very useful trick to deal with when working with negative signs. Then the other one is that fractional coefficients can be rewritten in a lot of different ways for the same type of reasoning. So you can either write 2/5, you can write, so I should write example here, example, and then an example here. 2/5 x, depending on the circumstances, could be written as 2x/5. Or you could write it as 1/5 times 2x, or 2 times 1/5 x, or 2 times x/5. Now, I don't know why you do the ones that I put in parentheses, Those ones seem like kind of a weird situation. But just know that because of the fact that we can write x, we can write any number as a fraction, we can put the x in the numerators should we choose. That's just a very, very useful trick for dealing with these things so that you don't have to deal with the fraction unless you really want to. So the key trick for solving linear equations that involve with fractions, in fact, with any fractions that you have to deal with, is to multiply by the LCD, multiply both sides, by the LCD, and we're gonna finish that statement in just a moment. But the key trick for solving linear equations, in fact, any equation with fractions, is to multiply both sides by the LCD. Now, why would we want to do that? Yes. So I'm glad to bring that up. So I'm not going to say like trying to find a common denominator by like making them into common denominators. I'm saying just multiply both sides by whatever number is the LCD. Because remember, an LCD is the smallest big number that all the denominators go into. Meaning that when I FOIL it in, when I distribute it in, excuse me, I meant to say distribute. When I distribute it into every single piece, since all the denominators can go into that LCD, all the fractions will cancel. So multiply both sides by the LCD. We should underline both so that all fractions cancel. And I'll show you what I mean with this first example. So you multiply both sides by the LCD to get rid of all the fractions. In this first one, what is the LCD? 30, yes. The LCD is 30. Because that's the smallest big number that 5 and 6 go into. You'll notice this a couple times, by the way. If numbers are what we call relatively prime, so a prime number, if you don't remember, this always bugged me, and I still think about it. So way back when, do we all remember the Falcons Patriots Super Bowl? It's a great time. It was a very, very silly situation where they lost that lead. But there was a big argument during that time period for who was going to be the MVP. And I disliked this man a lot, but Aaron Rodgers was in the running. And if you know Aaron Rodgers, his number for Green Bay was the number 1. And they were doing these stupid meme things to talk about who should be the MVP. And they're saying Aaron Rodgers, number 1, the first prime number. And that is when I lost it a little bit. I broke my 1 is not a prime number. 1 is not a prime number. By definition, a prime number is a number greater than 1 whose only divisors are itself and 1. So 2 is a prime number because the only numbers that go into 2 are 1 and 2. 4 is not a prime number because 2 and 1, 2 goes into 4 and so on and so forth. But back to the point, relatively prime means that the two numbers share no common factors. So if the two numbers share no common factors, like 5 and 6, then the LCD will just be the product of those two things. Pretty nifty little trick. But either way, that's just a random aside. So if I multiply both sides of this equation by 30, when I distribute it in on the right, I'll deal with that in just a moment. But look what happens on the right-hand side. The 30 and the 6 are going to cancel out because remember, this is 30 over 1. And remember from last time, we can cancel vertically and we can cancel diagonally. So we can cancel the 6 and the 30 just a little bit. So we know that the right-hand side is going to be equal to 5 times 5. We've gotten rid of the fraction, so it's just going to be 25. On the right-hand side, I'm going to do this step in one part. So it's going to be 24t plus 60. Let's take a second to digest that. Why is that true? Why is that true? The distributive property, yes. And the main one that I like that you might be wondering is how did I get 24t? Oh, yes. Exactly right. So the mental math that I'm doing, so for this one right here, in case you don't see it, and that's okay if you don't, the reason, when I distribute it in, I'm going to get 30 times 4 over 5. And what's going to happen is the 5 and the 30 are going to cancel. I'm going to get a 6, and then 6 times 4 is 24. That's what's going on. I'm doing that in my head. I don't expect you to be that quick at it just yet. But the other thing to keep in mind is you do have a calculator. So you can always just plug into your calculator 30 times 4/5. And I guarantee you, you'll get 24. If you multiply by your LCD and all the fractions do not cancel, you showed like your LCD wasn't correct, or you did some incorrect arithmetic. But this makes it into a linear equation with just integer coefficients, which is far nicer to deal with. So that's the key thing, is to multiply by the LCD to get rid of all the fractions. And then it's just like normal. So we're going to subtract 60 from both sides. We get 24t. So I'll write that down. So minus 60 from both sides. And then you'll get 24t is equal to negative 35. At which point we will divide both sides by 24 and get that t should equal negative 35 over 24. And that shouldn't reduce. The only factors of 35 are 7 and 5, and 24 are just 2, 4, 6, 8, and 20 and 12. 3, 4, 6, 8, 12. So nothing simplifies, and that's our answer. So this is a very, very common tactic that I like to use, especially if I'm dealing with equations that have fractions. I just multiply by the LCD so I don't have to work with them. It's not that I'm not working with them, it's just I'm finding a way to work around their nuances. Like when I was a barista at Starbucks, I had a closing shift manager, very, very delightful person, but she would talk forever. And so frequently we were supposed to be getting out at 10 and we would be getting out at midnight because she would be just talking up a storm. So I figured out the way to deal with it was just to be constantly busy and never talk to her, just be in a completely different room. Nice girl, very, very awesome. But either way, that's how I learned how to deal with my fraction situation there.
Into 6, why is it not 6 times 2?
With the right-hand side and left-hand side, right here. So this 30 is the same thing as 30 over 1. So when I can cancel diagonally, but now so the 5 goes completely away, and so now all I have is just numerator fractions. Maybe I'm misunderstanding.
So you're canceling out the 30 into 6, right? And then why isn't it times 2 in the fraction?
Excellent question. Excellent question. So what, like, are you talking about why this becomes 60 essentially? So remember, this is distributed into both terms separately. So the 30 goes into the 4/5 and also into the 2. It does it like so it becomes two separate things. There's a median step that I did not write, and thank you for bringing that up. So what ends up happening, this little middle step, is that I get 30 times 4/5 t plus 30 times 2 equals 25. Does that make sense? So that's the distributive property. Thank you. Ronnie. Ronnie brought up a great point. So you can write that step if you'd like to. It's like as much algebra as you feel comfortable showing, as much, and you can skip as much algebra as you'd like to. Any other questions? That was a good point. That was a good point to bring up. All right. Next one. What should I do with B? What should I multiply it by? 20 would be the right choice because that's the LCD. You could also multiply by 40, just like we talked about last at the very, very end. Remember that you can technically, you don't have to find the LCD. You can just multiply all the fractions together to get rid of it, right? So we could do 4 times 10 and multiply both sides, and that will cancel it out. But it's usually better to work with it if you just do the LCD. So the LCD here would be 20. So I'm going to multiply both sides by 20. And the way I typically write it, especially if it's like this, where I don't have to distribute, right? There's only one thing on the left-hand side, one thing on the right-hand side. And so I can do that. On the left-hand side, the 20 cancels with the 4 just a little bit and gives me a 5. And so now this 5 gets distributed in. Now that I've canceled it a little bit, I can take whatever's left and distribute it in. Similarly, for the right-hand side, the 10 and the 20 cancel mostly, and I'm left with the 2, and I have to distribute that 2 in. So I end up with 10z plus 15 is equal to 10z minus 2. Is that right? Did I really choose this one this way? Okay. This is good. This is a good thing. I think I did, like, I just forgot about the fact that I did this. Okay. So we try to solve this just like normal. And we're going to ignore that my voice cracked there, and just move onwards. And so we'll try to subtract 10z from both sides. You could bring everything, like you could do the multiple steps at the same time, right? We could subtract 15 from both sides if you wanted to at the same time. But either way, if we do this, we get an interesting situation. We get 15 equals negative 2. Does that mean we messed up? No, we didn't do any illegal math, right? We multiplied both sides with the same number. That was okay. We subtracted the same quantity from both sides. That's okay. That's legal. But when we did that, we ended up with a false statement. So what happens in that case? There's no answer. There's no solution. So the answer is no solution. This happens every once in a while, right? There are situations in life that do not have an answer, unfortunately. Yes.
What's the difference in no solution and undefined, or is there one?
So undefined is technically saying that there's no way to actually figure out what the value may be. There's no way to, I guess undefined and no solution kind of fit together here. I think they're synonymous in this context. We just usually say no solution because what we're trying to do in these problems is find a solution.
Well, I'm asking, I guess, more like on a test, it's going to be a question like this, and I put undefined, but it's supposed to say no solution down below.
No, I'll give you full credit either way. If you come to a false statement and you say it's undefined, that is also true. That means that there is no defining value of, in this case, z that will solve it. So the solution set is undefined because it doesn't exist. So if you get to a point when if you've done all your algebra correctly, I try not to make that happen very often. That seems like a rude thing to do during an exam when we're always trying to look for an answer. But if you get to that point, even if you made a mistake and you've checked your work out like 5 times and you still can't find out where you made a mistake, if you write no solution, you'll get full credit for the answer portion of the problem in terms of my partial credit, because you came to a false statement. And if you come to a false statement, that means that there was no way for this to work. Hence, no solution. Yes, excellent question.
Where you don't change the 30 into 6 for 30 times 2, but you did it for 5 times 3.
So, excellent question. There is a small, the difference is in how the algebra is flowing. So notice in the second problem, both terms in the numerator were being divided by 4, whereas in the first one, in part A, only the t was being divided by 5. So if all of them are being divided by the same number, then we can do, we can group them together and cancel first. You guys are asking some great questions. Keep it up. Love it. Any other ones? Right. The next one. Take a second. Don't say out the answer so everyone gets a chance to see it. Part C. What's the LCD? 9. Yes. Because remember, 2 and 4 are technically just 2 over 1 and 4 over 1. So finding the common denominator, there's not really, they don't need to be worried about. So we'll multiply both sides by 9. And then we'll distribute it in. And so on the left-hand side, that becomes 18 plus 3y equals 4y minus 36. And before I forget, I will talk about B one more time because I want to talk about what we call cross multiplication in just a moment. Any questions on the first step? It's okay if you have them. And please remember, use your calculator however you need. You're more than welcome to do that. I just want us to know that all the fraction work, how it works, how it's devised. Okay. Now, convention would be to bring the variables to the left, but I'm noticing if I do that, I'm going to get a negative y, right? If I subtract 4y from both sides, I'll get a negative y. And that's not wrong. We could do that, totally fine. But I like to keep my leading my leading terms, my highest powers of my variable positive. But you know what? Actually, I'm feeling silly today. Let's go ahead and subtract 4y. But you can definitely subtract 3y from both sides as well. However you want to do it is fine with me. But if I do that on the left-hand side, the 4y's, or sorry, on the right-hand side, the 4y's cancel. I get 18 minus y is equal to negative 36. At which point that's a positive 18. So in order to get rid of a positive 18, I have to subtract 18. That cancels it on the left-hand side. I get negative y equals negative 54, right? Feel free to use your calculator. 30 plus 10 is 40 plus 14, 54. Negative 54. Another math trick that I noticed is I saw 36 and 18. They're both divisible by 9. 36 is 4 times 9 and 18 is 2 times 9. So really that whole thing will be 6 times 9, which is 54. Random little math tricks that you can do. And then at which point, if you want to, you can divide by -1, or you can just immediately change the sign of both things. However you want to do it, I'll write it down, just dividing by -1 to cancel out that negative. And we get y is equal to 54. And then please remember, you can always check your work. So let me grab my calculator. And because this has variables on both sides, the way I would check it in my calculator is I would plug in the left-hand side. I'd evaluate the left-hand expression, 2 plus y over 3 at 54. I'd jot down whatever number I got, and then I'd write down, then I do it on the right-hand side, the right-hand expression, I'd evaluate it at 54 and see what I get. So for me, if I do 2 plus 54 divided by 3, I get 20. So I'll just jot that down on some scratch paper, or I'll write it lightly so I can erase it immediately. And then on the right-hand side, so I'll do 4 times 54 divided by 9 minus 4. Lo and behold, I also get 20. So I got the exact same number on both sides of the equal sign, making a true statement. 20 equals 20 is true. So that means I know I did it correctly. Before we do part B, D is going to be for the whole kit and caboodle. If you can do this one, you got a good grasp on all of your working with fractions and solving linear equations. But to talk about part B real quick, you don't have to write this into your notes. And once again, we talked about this beforehand. I was meant to delete this page, but I forgot to. But what was the equation? It was, can somebody read it out to me? 2z plus 3 over is equal to 5z minus 1 over 10. So there is another trick on what you could do in order to solve this that we call cross multiplication. So what what you can do, and what students will sometimes do, is they'll write this, and that's cross multiplying because you make a cross. Basically, the reason why, and so what ends up happening is you do 10 times 2z plus 3 equals 4 times 5z minus 1. I don't know why it's like slowing down, but either way. So you multiply the left numerator by 10 and the right numerator by 4. Now, why? Why does that work? It's mathematically valid. And the reason it works is all you're doing is you're multiplying both sides by 40. You're multiplying it by the product of the two denominators. And then on the left-hand side, you just get a 10. On the right-hand side, you just get a 4. That's what's happening. Now, I don't like cross multiplication, and I'll tell you why. It's fine to do. If you want to do it, it's that's your call. However, we have to be careful. Cross multiplication only works if it's a fraction equals a fraction. As soon as if I did this, cross multiplication no longer works. As soon as it's not a fraction equals a fraction, cross multiplication no longer works because, remember, I just showed you how cross multiplication works. You're just multiplying by the denominator, like the product of the denominators. So if I were to take this, let me erase the crossing out of stuff and making it confusing. If I were to add this plus 1 here, cross multiplication would mean that I have to distribute the 40 into that plus 1 too. Plus 1 as well, not plus 1 too. So cross multiplication is a great tool. It's quick, but the problem is it only applies to the situation where you have fraction equals fraction. As soon as you have like fraction plus a number equals a fraction, or fraction plus a number equals fraction minus a number, cross multiplication no longer works. So that's the reason why I typically avoid it. But if you want to do it on one of these problems where you just have fraction equals fraction, you're allowed to do so. Any questions on that? Plus, it makes it so you have to learn a new method. And one of the things you'll learn about me in this course as we go along is that I typically try to make my students memorize as little stuff as possible. I learned this, it took me until grad school to learn this, actually. One of my professors said, don't try, so in upper division math courses, it becomes less about procedures and more about proving things. You have to show why something is true. And there are thousands of proofs. And when you're taking an exam, the exam is going to be about all proving stuff. It's going to be question 1, prove this, question 2, prove that, question 3, prove this. And my teacher told me, he's like, don't memorize every proof. That's insane. That's impossible. Your brain can't handle that. That's too many things to keep it straight. The proofs are usually 3 to 4 paragraphs. Trying to memorize 15 different essays is a bad idea. He said, instead, look at it and figure out the crux of the argument. Figure out the crux, and you'll let your brain figure out the rest of it. That is the key thing to becoming a great mathematician, is remembering just one piece of information that makes everything fall from it, as long as you're willing to put your pen on the paper or your pencil on the paper. The trick for this one, the key thing to work with, is remembering to multiply by the LCD. If you can remember that trick, it all goes back to what we already know. So, anywho, back to this problem. The LCD is 12. The LCD of the left-hand side is 6, but we want the LCD of all the denominators. So not just the ones on the left, not just the ones on the right. Now, granted, you could multiply by 6. You'll just see that on the right-hand side, you won't get it. You'll still have a fraction. So you just have to multiply again. Not a big deal. It can still be done. But either way, I want you guys to slowly work through that problem. If you haven't done so already, I'm going to be filling in the details. Apologies. Or maybe I'm just getting older. One's a prime number, if I remember correctly. No, 51's divisible by 3. I have the answer up here if you'd like to check your work. If you're still working through it, continue to do so. This one's a long one, and this one, the answer does not look pretty. in comparison to the ones we've done so far. So I was skeptical as soon as I got my answer. It's like, seems like a pretty bad fraction. Usually these ones have been giving me nice numbers, but I checked it, as you can see in the blue at the very bottom, and I got the right answer. Right. So once again, we multiply by the LCD, and I tried to color code it just a smidgen. Hopefully you can see it a little bit better if I zoom in. So when I multiply the 12 into the left-hand side, there's two main terms. There's the 1/3 y minus 8, and then there's the 3/2 5y minus 5. So I distributed into both of them. And I decided to do it in two different colors so you can see. When I distribute the 12 into the first set of terms in purple, the 12 and the 1/3 cancel and give me just a 4. And I could go further if I wanted to, but I'm just going to stick with that for now. And then I did the same thing again in blue, the 3/2 and the 12. When I distribute that in, oh, I didn't mean for it to zoom like that. When I distribute that in, the 12 and the 2 cancel and give me a 6. And then the 6 times the 3 gives me that 18. But remember, you can always use your calculator, especially with some of these not nice fractions. You can definitely use it. Don't waste the brain space. Focus on the main problem at hand. And so I get 18, and then the 5y minus 5 hasn't been dealt with yet because of the order of operations. I'm working left to right. I'm taking care of the multiplication as I see it. And then on the right-hand side, the 12 is just immediately cancel, and I'm given a 7. At which point, now I can distribute the 4 into the first two terms, and I distribute the negative 18 into the second two terms. On the left-hand side, I get 4y minus 32. 18 times 5, the way I thought of that, by the way, if you want to do the mental math, the way that works is, and this is what they're trying to teach in the school systems now, instead of, I remember I got into an argument with a person on Facebook, and this is honestly what made me trying to delete it, because I just couldn't handle dealing with this type of person, because they got angry for them trying to teach multiplication a different way. And they said, like, what's wrong with the algorithm? It works. And my response as a mathematician was, well, why does it work? Why is this how we do multiplication? You go, okay, 5 goes into 8 40 times. And we just get a 0. And then 5 times 1, that's 5. So it's 90. Why? Why is that the method? Why does that work? Does anybody know? Yes, why exactly is the method of what we do? Why is it that we have to put the 4 up here and deal with it? Why is that the way it works? And the answer is you're doing distribution. What you're doing, and so this is the nifty little math trick that we're trying to teach kids, is that 18 times 5, you can break up the 18 into a 10 plus an 8. Because 10s are really nice to work with. So then I distribute the 5 in. 5 times 10 is 50. 5 times 8, that's a nice number to work with. That's just 40. And then boom, 50 plus 40, 90. That's the way, that's the mental math trick that I like to use. Now, of course, we're not needing to do mental math. We've got a calculator, but just in case you were curious, I remember trying to talk to him about that, and he just got angry with me when I told him, well, why does it work? Why? Because, yeah, you memorized it. You were good at memorizing the technique, but I can count on maybe one hand the amount of people who have asked that, and they know exactly the reason why the algorithm works. And it's like, then it wasn't a good way to understand mathematics. If it's just because you told me to, it's not a good reason. Anywho, I'm getting sidetracked. Then we got this, so 9 minus 90, and then the negative times the negative makes it a positive, right? Negative sign being distributed in changes all the signs, flips them, and then equals 7. Combining like terms, we've got a 4y and a negative 90y, which ends up being a negative 86, and negative 32 plus 90, that ends up being positive 58. Right-hand side has nothing to simplify, it's still just 7. Subtract the 58, then divide by the negative 86 to get our final answer. Because we get a negative divided by a negative, it results in a net positive of 51/86. And then what I did is I plugged it in my calculator. I plugged in the left-hand side. I ended up getting 7/12. The right-hand side, I didn't need to plug in anything because there were no variables on it. But if there were, I'd plug it in, and I get the exact same number, which means I know I did it correctly. Cool. It's okay if it's not cool. All righty. Then we'll move on to Unit 4. One of my favorite sections. I love polynomials. I love polynomials. Polynomials are one of the coolest types of things in mathematics. To give you a reason why do we study polynomials? Why are they important at all? There's a lot of things that happen with polynomials. Polynomials are the building blocks of a lot of things. You can, a lot of real life situations, we require variables to describe them. And in order to figure out where to maximize and minimize things, we need to be able to work with how to deal with polynomials, how to add and subtract them, how to FOIL them together, how to multiply them together, how to factor them. All those things are very, very valuable. Now, if you want to go even further, this is the really, really fascinating thing. Just to go on a quick little side detour, so don't write this down, but I'm sorry, I just got to gush about it for a second. I got to gush about it because it's just such a cool thing in mathematics. There's a thing called the Stone-Weierstrass theorem. This is a very, very big theorem in mathematics. It requires you to be in 400 level mathematics or above. You might learn about it in real analysis in your 4th year of college, or you might have to wait until grad school to talk about it. But it's a fascinating theorem. What it says is that any expression you want, I'm going to bring it down to our level. It becomes a much more nuanced situation. But basically, what it says is that any expression you can think of, anything at all, can be approximated within a very, very, very close reason of certainty with a polynomial. And that might not seem like a big deal, but the fact of the matter is polynomials are very nice to compute. They're not too terrible to plug in numbers because it's all just dealing with exponents and multiplying numbers. Whereas if I'm trying to ask you what the square root of 1/2 plus pi is, this becomes a very, very daunting task to figure out what the approximation of that number is. If you've ever wondered how your calculator computes it, it uses a different version of the Stone-Weierstrass theorem. So it's a really cool concept that you can take just a big enough polynomial and it will magically give you that number. That's really, really fascinating to me, at least. Then again, I'm biased because this is what I love to do. So anyways, that is why we like to study them. We study them because of how many things that they can do. So the definition section, we're going to have a bunch of definitions just because we need to know about the terminology in order to work with them. So first one, get ready for a mathy definition. A polynomial is an expression of the form a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus dot 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 plus a sub 2 x squared plus a sub 1 x plus a sub 0. Okay, take a breath. It's scary, I know. Believe me. Like when I first encountered this type of terminology, it freaked me out as well. But we're going to talk about it once you've written it down. So a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus dot 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 plus a sub 2 x squared plus a sub 1 x plus a sub 0. This is what we call general form. This is a common thing in mathematics, these ellipses. The dot 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 is for a specific reason. Mathematics, we love to describe things as generally as possible. We like to say an overarching statement that can be applied to any situation. So polynomials come in all shapes and sizes. You can have a 55-term polynomial. You can have an 80 billion term polynomial. You can have a 1-term polynomial. So how do we write a definition that encompasses everything? And in order to do that, we have to be very general. And in order to do that, we have to use variables to represent fixed numbers. So n is some positive integer, and then a sub 0 through a sub n are numbers. So that's the scary version of it. And so if I'm dealing with a generic n for my exponent, then that means that I can't figure out how many terms I have. Because n could be 5 billion, it could be 1. And how do I know which one to do? So that's why those dot, dot, dots are there. We write it so that we see the first couple terms and see how the process is working. And then say the dot, dot, dot is saying continuing this process until we finally get down to nothing. Until we get down to the a sub 2, then the a sub 1, and then the a sub 0, because we don't know where we started, to make it very, very generalized. That's how that terminology is described. Yes. What is A?
You saying A or A?
A sub n. So A subscript n. So this right here, this is A subscript n. This is A subscript n minus 1. This is A sub 2 or A subscript 2, A subscript 1, and A subscript 0. That's sorry. Thank you for asking that. The short notation, the shorthand state is A sub n, but technically speaking, we should say A subscript n. Just once again, mathematicians being very lazy about things, not wanting to have to say more than we have to. But yeah, it's the subscript is to say these are each individual variable, each individual numbers. And you might be saying, well, why didn't you just use different letters to represent the numbers? And it's because this is generalized. What if there's more than 26 numbers? What if there's more than 26 terms? We only have 26 letters in our alphabet. And then you might, well, but then go to the Greek numbers, go to the Greek letters. But then we only have 52, and we can only do a 52-term polynomial. What if I want a 100-degree or a 100-term polynomial, and so on and so forth? So in order to avoid that, we just use subscripts. So that's how that all works. That's the scary version of the definition. That's the big boy. That's the big boy definition of what a polynomial is. But we don't need to be using that terminology too often. But that's what it generally looks like. But the key requirements that that you can parse through this information for is that all exponents on the variable portions are whole numbers. 1, 2, 10, 15, 6,000. It doesn't matter, but they're all going to be whole numbers, positive numbers, positive integers. There are no variables in denominators, right? This is just a single line of things with no variables in denominators, and there's no variables inside radicals or other grouping symbols other than parentheses and technically, I guess, brackets, because a bracket and a parenthesis are the same thing. It's just for readability's sake. So we're going to go through a list of looking at polynomials and seeing which ones are and which ones aren't. So 5x squared minus 2x plus 1, that's an example of a polynomial. All the variables are being raised to integer powers, positive integer powers, and we're all good. Whereas the next one, it says 3xy to the negative 2. The negative 2 is what's causing an issue. That's the issue. The 2x squared, the plus 1, those things are fine. If I got rid of this term, it would be a polynomial. If I got rid of this factor, it would be a polynomial. If I got rid of this exponent, it would now be a polynomial. Next one, 2xy squared plus 3y squared z cubed minus 8z.
Why is that?
So in order for it to be a polynomial, exponents always have to be exponents on variables need to be positive numbers. And there's a great reason why. It's as soon as you start using negative numbers, then you have to worry about dividing by 0, right? We'll explain that when we get to the exponent rules. But a negative exponent can mean that you get something that's undefined when you plug in a value. For example, if I plug in y equals 0, if I evaluate this polynomial at x equals 1 and y equals 0, your calculator will say a math error. It'll say it doesn't exist. Whereas if I plug in any number into this term right here, I will always get something. I will always get a number back. That's another thing about polynomials, is that they are always defined. That's the key thing. No matter what value you plug into a polynomial, you will always get back a number. That's not true with 3xy negative to the negative 2. This one right here, polynomial. All the exponents on the variables are raised to whole numbers, and and there's no variables in denominators. There's no variables inside of radicals. With this next one, this is the issue. This is why it's not a polynomial. We have variables inside of a radical, and that means that we start having to worry about things not being defined. The next one, negative 3x cubed minus 9 over 8. That is also a polynomial. And you might be saying, well, Phil, you said no variables inside a denominator. It's okay for numbers to be in a denominator. That's okay. Because remember about the distributive property, right? You can just rewrite this as negative 3/8 x cubed minus 9/8. And so it's okay to have fractional coefficients, like the numbers in front of the variables. That's okay. It's just you can't have variables in denominators. Hence why this next one, this is the issue. We have a variable inside a denominator, and that thing is no longer defined. If you try and plug in 5 into this expression, 2 over y minus 5, you'll see that you get a math error. You get 2 divided by 0, and we talked about it on the first section. Any number divided by 0, any non-zero number divided by 0 is undefined. The next one, square root 2 over 2 w minus 1. That is a polynomial, but it's got a radical. Oh, wait, no variables inside of a radical. Square root 2 over 2, that's just a number. It's an irrational number. It's one that doesn't irrational numbers are numbers that have a non-terminating, non-repeating decimal expansion. So pi is irrational because it goes 3.14159.6, blah, 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 and it never repeats itself, and it just goes on and on and on forever. You know, honestly, never talk around with pi. It just goes in circles. Right, there you go. It's an irrational conversation from the start. Great joke. But the point is, square root 2 over 2, that doesn't have any variables inside a radical, so it's fine. It's just a number in front of a variable. That's okay. The next one is not a polynomial because of the 3/4. The 3/4 power is the issue. We need all of our exponents to be raised to whole numbers, positive integers. So if I got rid of the divided by 4, right? If I did this, then it'd be fine. Then it's chill. It's all good. Or if I get rid of the 3 there, then it's all chill, but not in its current standpoint. The next one is just supposed to be an interesting kind of discussion. 22 is a polynomial. It is. It's not a very exciting polynomial because it's just a number, but technically speaking, any number by itself is a polynomial. 3 over z, because remember, that's technically 3 divided by z. And that raises our issue. That's going to be, that looks like a 7 instead of a z. That's the issue. Any questions on that? So key things to keep in mind, polynomials, they have to be all variables raised to positive integers, no variables in denominators, no variables inside radicals. Later on, we'll also talk about like logarithms and stuff like that. But for now, that's all we have. So those are the conditions that we'll describe not polynomials. And the next definition, this is honestly not really a definition. It's just more for terminology's sake. Kind of like how, I guess, technically speaking, numerator and denominator are definitions, but it's really just so we can talk about what a fraction is in terms of its parts. So this is kind of like a less important definition, but still useful. There are 3 special types of polynomials that we encounter a lot, which are based on the number of terms on them. We have monomials. these are one-term polynomials. So for example, we have like 5x to 13 halves x squared y, etc. Those are all examples of monomials. They are one-term polynomials. And you have, and so this is where we're using, I think it's Latin roots, I think. We have binomials. And binomials are two terms. So things like x minus 7, z cubed y minus 8, w, v squared plus 4, etc. They're all two terms. You can write as many as you want here, but a binomial is a two-term polynomial. And the last one that that's very common are trinomials. So that's three terms. So something like x squared plus 2x minus 3, or x plus y plus z, etc. As long as it has three terms, it's a trinomial. Now you can say a two-nomial, a one-nomial, a three-nomial, or four-nomial. You can continue this process knowing all of our kind of, like, I don't know if it's Latin roots, but regardless, like Latin roots essentially, like you could say a quadnomial is 4 terms, a pentanomial will be 5 terms, a hexanomial will be 6, and so on and so forth if you really want to do that. However, I'm hoping we can eventually change that as a society. I disagree with us trying to teach kids to memorize the names of the shapes as like a pentagon, a hexagon, a heptagon, an octagon, so on and so forth. Just call them the number they are. A 5-gon, a 6-gon, a 7-gon, an 8-gon. It makes way more sense, right? Why do I have to make my students, like my kids, memorize all these new names when it's meant to be a classification? So actually, well, that's what I'm doing with my son, is I'm calling them like, yeah, that's a hexagon or a 6-gon because it has 6 sides. It's actually one more side note, just one more thing because I'm frustrated about it, is make X make a X sound. It's no longer a xylophone, it's a xylophone. Please. It's so stupid seeing the children's books and it says S is for salt and so on and so forth. Then an X makes a X sound and it's for xylophone, as an example. Why? That's so confusing to a kid. That's such a weird concept. Same thing happens with well, we can talk about that during the break. That's another one. I don't want to get too distracted, but we can continue on with this. We can do quadnomials and so on and so forth. But as soon as you kind of go above 3, you just start calling it a polynomial, or a 4-term polynomial, 5-term, so on and so forth. Now, the degree, and this is the next one. The degree of a term so I'm being very, very clear, very, very particular. The degree of a term is the sum of the exponents on the term's variables. There should be an apostrophe there on the term's variables. The degree of a term inside of a polynomial is the sum of all of its exponents. So if we're looking at this polynomial here, negative 5x to the 7th plus 4y minus 2/3 x y z x to the 5th y z cubed plus 15. So the terms are negative 5x to the 7th, 4y, negative 2/3 x to the 5th y z cubed, and then 15. Those are the terms. And the degree of the term is the sum of the exponents on the variable portions. So the first term, the degree of it is 7. What's the degree of 4y? 1, yes. This is one of those things, once again, mathematicians are very lazy. We don't write an exponent of 1 if it's quote unquote assumed from the context. So the degree is 1 because there's a implied 1 here. What's the degree of the next term? JT says 9. He's absolutely right. Because remember, that's 5, that's x to the 5th, y to the 1st. So it's going to be 8, or sorry, 9. And the reason for that is it's going to be, and I'm going to highlight them actually. So it'll be 5 plus 1 plus 3. That's the reason why that term's degree is 9. And then 15. What's the degree of 15? It doesn't have a variable portion. So it's going to have degree 0. And we can explain why once we get to exponent stuff. But in particular, you can think of that as 15 times x to the 0. And so the variable portions, the exponent on the variable portion would be a 0. So any constant's degree is 0. Any questions on that?
In the top definition, polynomial,
Mhm.
what's the difference between a subscript and a superscript?
A subscript is in the bottom, a superscript is in the, oh, besides that. So a subscript, we only ever use in mathematics a subscript to be able to identify individual elements, whereas a superscript, unless there are very, very, very niche situations where this would happen, but almost like for us in this course, and basically anything unless you get into grad school, it will mean an exponent. As soon as you like, there are certain situations, there's a thing called Einsteinian notation for differential geometry. And in that course, it means something, it's kind of like a subscript, but for us, any superscript will be an exponent. Great question. Very, very good question. I had to do, I like in my thesis, I actually had to use, this is a fun little tidbit. In order, I couldn't write my one of my problems. I couldn't write one of my expressions on one page. It wouldn't fit. So, and I couldn't figure out how to fix it. So I said, screw it, I'm going to make my own notation. And my notation was delta. So the Greek symbol delta. And then I did a subscript N, and then that subscript had I and J, and then M to the I, to the K and L. So I had a double superscript and a double subscript. It was like my thesis advisor did not like it, but we accepted it because I couldn't write it on one page. I would have had to turn the page sideways and do landscape if I really wanted to. But so yeah, subscript in short. Sorry for the detour, but in short, subscript is for identification of different elements, whereas superscripts are for exponents. Okay. That's the degree of a term. The degree of a polynomial is different. The degree of a polynomial is the largest degree of all of its terms. So looking at this previous example just for a quick second, the degree of that polynomial is 9. The degree of each term is separated, but the degree of the polynomial is the highest degree that you see, which in that case would be 9. We call and this is kind of a sub-definition, is that we call the largest degree term in the polynomial, we call that the leading term. Or I guess you could say lead term, but most people would say leading term. And the coefficient, the number portion on the leading term is called the leading coefficient. Now, why would we care about that? Why would I make you memorize this terminology, leading term and leading coefficient? Why is that necessary? That's a great question. I'm glad you asked it, Derek. It's a great question. When we get to unit 2, which will be on polynomial functions, we'll get to that soon enough. We'll get to know what a function is soon enough. But when we get to that, we're going to be studying a thing called end behavior, and end behavior comes from the leading term and the leading coefficient. So there is a reason to talk about this. It's not just because I want you to memorize fun math terminology so that you can sound better than everybody else. That is part of it. That is part of it. We always want to sound cooler than everybody else. That's why we want to know the word vacuously satisfied and grande macchiato instead of a medium macchiato, right? You want to sound better than everybody else. That's the key. Of course, kidding. Okay, so looking at the time, let's take a break and we'll talk about degrees and then we'll talk about algebra with polynomials. Let's come back at 10:16. People watching the lecture, go take a stretch, do some guided meditation, whatever you want to do. All right, we're back from our fun little detour. So once again, degree of a polynomial is the largest degree that you see amongst all its terms. So we're going to determine the leading term, the leading coefficient, and the degree of each polynomial. Oh, that's a typo on part B. This is supposed to be 5yz cubed, like that, not 5y to the z cubed. First one is degree six. Degree 6, and its leading term is 17x to the 6th. Its leading coefficient is 17. Part B, the degree of the first term is 3. The second term is degree 4. And the third term is degree 2. So the largest degree term is 4, so the degree is 4. With a leading term of 5yz cubed, and the leading coefficient is a 5. Yes, JT.
That's supposed to be 5y to the second, z to the third.
Oh, it was supposed to be. It was supposed to be. We'll just do 5yz cubed for now. But yeah, when I go through and edit this, it will be 5y squared z cubed, which would make it degree 5 instead. But either way, this works. The interesting case with multiple variables is what happens if you have a term that's 5xy squared and one that's x squared y. Those are both degree 3 terms. Which one's the leading term? That's a gray area that we won't really cover because that's upper division mathematics. We're only talking about multivariable polynomials just to get practice with dealing with them. Multivariable stuff, that happens in your second year of calculus, is when you start talking about multivariable stuff. We're only going to be dealing with single variable, other than just simplifying polynomials. Any questions on that? All right. In order to do algebra with them, thing to remember is that in order to add and subtract two terms, they must be like terms. And as a reminder, what that means is same variables to same exponents, to exactly the same exponents. It's not enough for it to be x squared y and xy squared, right? Yes, they have the same variables, they have the same types of exponents, but they're not attached to them properly, right? Let me write that down so we can see it. You don't need to write this down, but these are not like terms because they're the same variables, same exponents, but not in the right order. It needs to be x to the first power, y to the second power in order to be a like term to the first one. So, the other thing I'll mention is that we typically like to see our polynomials in either descending order of degree or in ascending order of degree. So it either goes up to the highest degree or down to the lowest degree, depending on the situation. I usually like to write mine in descending order But there are a few nuanced cases where it would make sense to write it in ascending order, but very few and far between. I promise you on my exams, they will always be listed in descending order. So you don't have to worry about like trying to find the degree term in the middle. It will always be the first term for me because I don't think that's a very fair thing to do to students. To try and trick you up with that. That seems like an unnecessary thing. But ideally, we like them in descending order. So this first one, 3x squared plus 3x minus 5 plus the quantity x squared plus 4x plus 7. Now here that those parentheses are kind of redundant. They don't need to be there because there's nothing to distribute in. So we can kind of just drop them. And this becomes 3x squared plus 3x minus 5 plus x squared plus 4x plus 7. And so all we need to do now is just look for like terms. And you can either underline them or you can work through it one by one. I've had students so there are many different ways that work for students. One way students have done it in the past is they go down the list. So they look for all the x squareds first. And then they write, so this is going to be 4x squared. And then what the students do is they'll just kind of cross them out as they go through. That's one way to do it. I've always been a fan of just underlining them in different colors. So I found all the x squared terms. 3x squared plus x squared is 4x squared. And there's a 3x and a 4x that are being added. So it's going to be plus 7x. And then we have a minus 5 and a plus 7, which is a net positive 2. And that is listed in descending order. Goes from its highest degree term, which is degree 2, then degree 1, then degree 0. What's the degree of that polynomial? 2, because it's the highest power. On the flip side, with part B, the parentheses on the second set of terms, this trinomial here, is necessary because that minus sign needs to get distributed. So let's write that down right now. That minus sign needs to go into all three of them because that's really the same thing as multiplying all those terms by -1. So go ahead and start working through it. I'll slowly fill in details. You should get, for the second one, you should get 25z cubed plus 4z minus 31. Again, feel free to use your calculator wherever you don't want to do too much arithmetic. If you want to let the calculator do the heavy lifting there, that's fine. This is a degree 3 polynomial, but it doesn't have a degree 2 term. That can happen. It can be that you only have the highest degree term and a constant. That happens too. So every polynomial is unique. All right. I'd like you guys to do C and D. And I'll slowly fill in details if you haven't already started working on them yourselves. So all the properties we learned before, they still apply. Distribution, all that stuff. the doozy, but you do this, you can do part A again. I forgot to make it as a typo. And if you're sitting there thinking there's no way that this would ever really show up ever again, this seems like a just Phil trying to pull my chain on something. It's not true. This is something that you'll do if you decide to go on into engineering. You're going to have to take a course called differential equations. And I think I mentioned it before, but like there's a thing called the method of unknown coefficients, where you have to kind of work with polynomials this size, and you have to combine them and figure out what should be what. So. We'll use parallel. I have the answers to part B, C, and technically it was A, but C and D if you'd like to check your work. Slowly go through the details. Part C, it's all about distribution. You got to distribute the 2 in, and you got to distribute the -7 in. So you get 2x squared plus 2x minus 16 minus 7x plus 35. And then combining like terms, there's no like terms of the 2x squared, so it just sticks around. Then I move to the next term and try and find any common terms with it. There's a 2x and a -7x, resulting in a -5x. And then -16 as a common a like term of 35, which ends up being 19. Next one, the first set of 3 terms, the first trinomial doesn't have any thing being distributed into it, so we can just leave it alone. The 2 gets distributed, giving you the 6y squared minus 10y plus 14. And then with the quadnomial, the 4-term polynomial in the last set, that minus sign gets distributed in, which gives us plus 4y cubed minus y squared minus plus 12y, and then plus 1. So then I have to go through and combine like terms. When it gets to this size, honestly, I was looking at that and I had to really check my work several times. So if this was the situation, I might start going through it and canceling it once I've done it. So I go through all the red ones and then I just cancel those out. I just say, okay, those are all done. Then I did the blues, -2y minus 10y, that's -12y plus a 12y. That cancels out everything. There's no more y's left. So that's gone. And so I could cross those out myself. Boom, boom. Then I'll move on to the greens. 3 plus 14 is 17, plus 1 is 18. So those are done. And then the only things left are the pinks. So 6y squared and minus y squared, that's a plus 5y squared. So initially, if I did it right in that order, I would get 13y cubed plus 18 plus 5y squared. However, I'd like it written in descending order because that will be very, very useful when it comes to factoring. So we'll get to that next week. So I'll write it in descending order. So that should be 13y cubed plus 5y squared plus 18. Any questions on that? All right. So next thing are some exponent rules. Some rules about how exponents work. And this is going to be true for any quantity. It's not just for numbers and letters. It could be expressions. You could have x plus 7 raised to the 3x minus 9. That's possible. Weird, but it can happen. So the first rule, a to the m times a to the m. Notice that they have the same base. You write that if you want. Same base. If you have two things being raised to the same base, like two things with the same base being raised to different exponents, it could be the same exponent too. You add the exponents. So this becomes a to the n plus m. So as an example, if you have x to the 5th times x to the 7th, that becomes x to the 12th. Because that's going to be 5 plus 7. But they need to be the same base. As soon as it's something like this, if it was x, so don't write this down. This is not correct work. If you add x to the 5th times x plus 7 to the 7th, these things cannot be combined because they don't have the same base. And if you have any questions why these rules are true, please feel free to ask. I'm happy to go over them. Similar situation, if you have a to the n over a to the m, once again, same base. Then it equals a to the n minus m. You take the difference, top minus bottom. So I'm going to give two examples here just to show some weird situations that may happen. If you have y to the 3rd over y, that would be y to the 2nd power. That's going to be 3 minus 1. Additionally, you could have something weird like this. You could have x to the 5th over x to the negative 2. We didn't say that it couldn't be a negative number. It could be any quantity. You could even make it x to the x. And regardless of how that works, regardless of what the quantity is, it's always going to be, if you have the same base and they're being divided, you take the difference of the top and the bottom. So this would become x to the 7th, because that's 5 minus negative 2, which would be 5 plus 2, which is 7. Next one is that a to the n then raised to the m. So if you have a power raised to a power, you multiply the powers. This becomes a to the n times n. So let's say we have, for example, if we have parentheses, brackets, then parentheses, the quantity 2x minus 5 to the 3rd power being raised to the 4th power, like that, the answer will then become 2x minus 5 to the 12th power, because it's going to be 3 times 4. You're going to multiply the exponents together. Then, if you have a product of things or a difference of things, all being raised to the same power, you can, quote unquote, distribute the power in. So this becomes a to the n, b to the n. And therefore, if you have a over b raised to the n, that's a to the n over b to the n. Any questions on that? Let's do an interesting example here. What if I had x squared y to the 5th power? That would become x to the 10th times y to the 5th. Take a second to make sure you understand why it would be x to the 10th, y to the 5th. And if it doesn't make sense, feel free to ask. Take a second though. X squared. It'll be x squared to the fifth. So that's a power raised to a power. You multiply the powers. That's why it becomes x to the 10th. And then y to the first power raised to the fifth. That's 1 times 5, just to the fifth power. Then the last one, which isn't going to be super useful right now, but it is useful nonetheless, is that a to the negative n is 1 over a to the n. So you can convert, the big deal here is that you can convert negative exponents to positive exponents by writing it as 1 over a to the positive version of that number. So for example, if you have 2x being raised to the negative 3 power, that's the same thing as 1 over parentheses 2x to the third power, which would be equal to 1 over 8x cubed. And it's going to be 8x cubed because it'll be 2 cubed times x cubed, but 2 cubed is 8. Any questions on that? There's a lot of algebra that we can do here. There's a lot of different things we can do. This one has a couple tricky situations that we can work with. And I just like to highlight them for a second. What if I had, as another example, what if I had, what if I had 1 over x squared raised to the negative 2? So there's a lot of ways we could simplify this. There's many different ways. There are a myriad of options. My first thought would be to say, well, 1 over x squared by that rule. Remember, these are all equal signs. So they're true backwards and forwards. So we can either, so for this, for example 5, we can either be given 1 over x to the 1 over a to the something and convert it to a negative exponent, or vice versa. Same thing true. Same things here. If we have two things being multiplied together and they have the same exponent, we can combine them together. So these things, remember, these are equal signs, so they work backwards and forwards. So if I had this, my thought would be to write this as x to the negative 2 raised to the negative 2, which would be x to the 4th power. That's the way I would think about it. But there's another option. In an alternate explanation, you could do, or you could write it as 1 over x squared squared, right? The whole thing, the 1 over x squared was being raised to the negative 2. So by the property, that becomes 1 over this to the 2nd power. Then by this property right here, that would become 1 over 1 squared over x to the 4th power, because it would be 2 times 2, right? X squared squared. But 1 squared is 1. So this would be 1 over x to the 4th, which would therefore be x to the 4th. Remember, if you're dividing by a fraction, you flip and multiply, right? Gets you the same answer either way, but I'm just trying to show you that there are many ways to get to the same answer. Sometimes we get clever and we realize something right off the bat. Other times it's not as inherently clear to us, but you can still get there. Any questions on those properties? All right. In the interest of time, we're gonna do A, B, and well, maybe we can do all of them. Let's go ahead and work through all of them. Let's do A and B together. So A would then be x cubed, w to the 6th, y to the 12th. So all those properties can be generalized, not just being when it's A times B, you could write it as A times B times C raised to the n. So we have x to the third power, that stays there. We have w squared then being raised to the third power. So that's squared raised to the third. So you multiply the powers. That's why we got w to the sixth. And the same thing for y to the fourth. That becomes y to the 4 times 3, y to the 12th. Part B, that'll be negative 2 to the 4th times x to the 8th, y to the 28th. Because it'll be 2 times 4 for the exponent on the x to the 8th, and then 7 times 4, which is 28. But I'd like to simplify that negative 2 to the 4th power. You can use your calculator if you'd prefer, but that'll be negative 2 times negative 2, that's positive 4, times negative 2 again is negative 8, times negative 2 again is positive 16. So it should be 16 x to the 8th, y to the 28th. Part C, oh, Wes.
I thought for adding exponents, you would add them up.
So that's a power raised to a power. As opposed to, we'll see in part C, that's when the adding is going to come into play. Is that okay? Wes asks a great question. It's that we have a power, these are powers being raised to powers, so that's why we multiply them together. So with part C, I wanted to remind us about the order of operations. The order of operations says we need to take care of exponents first. Well, parentheses, but there's nothing really to simplify inside those two sets of parentheses. So we'll go to exponents. So this thing should start off as 2x to the 5th times 27x to the 6th. That's its first step. Because 3 cubed is 27. If you don't have that memorized, that's fine. But you can just use a calculator. 3 times 3 times 3 is 27. And then x squared being raised to the third power, that's x to the 6th, because it'll be 2 times 3. But now it's two things with the same base, the x's, being raised to two different powers and being multiplied together. So we add the exponents. So it'll be 54, because 2 times 27 is 54. And then x to the 11th. Any questions so far? It's okay. There are. I want to do D, and then I'll give you guys the answers to E and F, and then move on. So you can check these out over the weekend. So E will be negative 40 x to the 5th, y to the 10th. And the answer to F will be negative 3x cubed plus 6x squared plus 9x. So those are the answers to those two. Verify it on your own time. And put a little bit of space so you can work through it. And if you have questions about that, of course, you can email me. And then D. So 2x cubed, that's being distributed in. So we've got to distribute it. When we distribute it into the first set, the 2 and the 1/4 will cancel just a smidgen, and it'll give you 1/2. And then it'll be x to the 4th power, because it'll be x cubed times x to the 1st power. Add the exponents, we get x to the 4th. The next one, x and y are completely different bases, so we can't do anything to them. We just have to leave them separately. And so this will become minus 6x cubed y. And the last one will be 14x to the 0, because it'll be x to the 3rd power times x to the negative 3rd power. 3 plus negative 3 is 0, but x to the 0 is equal to 1. Anything raised to the 0 power is 1. Well, except for 0 to the 0. That's an interesting case. But that'll be 1/2 x to the 4th minus 6x cubed y plus 14. Any questions on that? realizing that we're not going to be able to finish all of today's material. We're going to have like a couple things left to do. We've still got to talk about multiplying binomials and beyond. So I'm going to extend the quiz and the homework for 0.4. 0.1 through 0.3 will still be due this Sunday, but since we didn't finish all of 0.4, I'm going to extend that until next Sunday. But you should be able to do most of unit 0.4 with everything we've learned today. But the quiz has a little bit of questions from the last part of it that we haven't covered yet. So I'll extend that until probably Wednesday so that we can finish up this. So let's go to the next thing. One last thing. So multiplying polynomials together, not just monomial times monomial or monomial times something else, but what about binomial times binomial or trinomial times trinomial and so on and so forth. The motivating example is how should we go about simplifying a plus b times c plus d? Because up until this point, we've only ever had it be a number or an x being multiplied into a group of things. How do we do it with this? So there are two main methods. So a plus b times c plus d. We could think of a plus b as its own quantity and distribute it in. So we take this a plus b and distribute it into c and into d, giving us parentheses a plus b times c plus a plus b and parentheses times d. And then, by a very, very similar argument, we can distribute the c in and we can distribute the d in. So we can go whoop, whoop, and let's use orange. We haven't used orange in a while. To give us AC plus BC plus AD plus BD. That is what is happening, technically speaking. That is the mathematics that's going on. But that's kind of tedious. That takes 2 steps and it takes a lot of drawing arrows and stuff. Who doesn't want to don't want to draw different colored arrows unless we have to? But one thing I want you to notice is that each term from the second set, the C and the D, got an A, right? Each term, the C and the D, had an AC and an AD. They also had a BC and a BD. So what's happening really is that each term in the first set gets distributed into each term of the second set separately. And that's what we call the FOIL method. When it comes to multiplying binomials together, binomials in particular, but this method can be generalized, we call it the FOIL method. So FOIL. So if I have, let's say, 2x plus 3 times x minus 4, why not? The FOIL method, F stands for first. So let's use. That's F for first. Outer. I is for inner. And then L is for last. We do the first terms multiplied together. We do the second terms multiplied together. We do the first ones multiplied together. Then we do the the I, yeah, the inner. Then we do the oh my God. No, okay, I'm good. First terms together, outer terms together, inner terms together, and then the last terms together. Thinking about it without all the color, just realize we've got, so what this should equal is 2x squared then minus 8x plus 3x minus 12, which simplifies to 2x squared minus 5x minus 12. So I will extend the due date. I'm sorry to keep you 1 minute late. I will extend the due date on that on unit 0.4 until next Sunday, along with the quiz until next Wednesday. So, I mean, if you want to work ahead and work on these problems, go right ahead. You can finish most of unit 0.4 now, but it won't be due until Sunday. But everything else, 0.1 to 0.3 is due this weekend. Okay? If you have any questions, please feel free to email me. We'll pick up next time with this. So if this is looking like gibberish right now, don't worry. We're going to go over it again and rehash it on Monday. Okay? Have a great rest of your day, a great weekend. Try to limit your social media exposure. Not real. People around you are the ones that matter, right? Avoid the endless scroll. It ruins your brain. Avoid the endless scroll. And have a great rest of your day.